So before we start this tutorial video, I just want to give a quick disclaimer. You should probably know what the chain rule is, right? Kind of important with kind of an important concept in derivatives. If you don't, I'm actually gonna have I'll have a link to Khan Academy's like really easy tutorial on derivatives that you can just go over in an hour or 2 hours of your time just to get a refresher on derivatives. And then come back to this video, because otherwise you're going to be a little bit lost. And in general, you should know what a feed-forward neural network is. I already did a tutorial on that, so I'll have that in the description also. But if you have a decent understanding of these two concepts, then this tutorial is for you. Otherwise, I would actually recommend you go to those two sources first, and then watch this video. So before I move on to the coding part, it's best if we are all on the same page. I'm going to explain it here, you know, some of the data structures that we'll be using, and just in general how backpropagation works, because that's quite important, so that when we actually go to program it, it'll make a lot more intuitive sense. So first thing, let's just get the same naming convention, because that would make it a lot easier for me when I'm explaining it. So if we're all on the same page in terms of the naming conventions, it would probably be a lot easier. So the first thing, the B means before activation. So you can kind of see in my diagram over here, I've written BH11 and then H11. So BH11 is the before activation, and then the H11 is after it's been activated. And the activation that we're going to be using is tanh. So that's just hyperbolic tangent, which just squashes our input down between -1 and 1. So basically H11 is the tanh of BH11. So just this example here, and then I expand and then I basically just expand over here in this formula right here. I expand out BH22, which is just H11 times W9 plus H12 times W10, which let's see if we can see that here. Yep. So H11 times W9, right, and then H12 times W10. That makes sense. My example naming convention, H12 is hidden layer 1, neuron 2. So where's H12? So see, this is the second neuron, and then the first layer, so H12. This is the second neuron in the second layer, so H22. So in my output, just O1, that's output 1, and then O2, output 2. And then my inputs, input 1, input 2, input 3, okay? So that naming convention is pretty straightforward. That's pretty much what I'm just going to be using as I'm explaining things. So, but I think actually dividing the before activation and then the activation part will actually help simplify our backpropagation just a little bit more. The error cost expression that we're going to be using is mean squared error, which I expand out over here. So for an example output of y1 and y2, the mean squared error is just going to be O1 minus y1 squared divided by 2 plus O2 minus y2 squared divided by 2. So this is essentially just equal to our total error. And this is how we can kind of evaluate our neural network over time. So maybe you know, we expect to see the mean squared error go down over maybe 1,000 iterations of training on some data. And if we see our mean squared error go down, then that means our neural network is actually learning. Of course, we don't have to use mean squared error. We can use other cost expressions such as log loss, things that are specifically designed for categorical outputs. So there's plenty of other cost functions, but in this case, we're just going to stick with mean squared error because that's the most common cost expression that's used with neural networks. So now what I'm going to actually attempt to do is actually augment something that I write in real life along with take a screen recording. I've never done this before, so I hope that it works first try. One thing that I'm just going to say really quickly is the derivation calculations for the output layer in our code will be a little bit different than the derivation calculations for the hidden layers. The reason for that is because the output layers is where the error cost expression is first calculated, and the hidden layers are essentially the backpropagation of the error cost expression. So essentially the outputs is where we're going to be passing in this y1 and this y2 information so that it can do the first layer of derivatives. Let's just do a derivative for one of these weights, I mean in the output layer, it's good to expand out the chain rule and actually see what happens. Try to do the derivative for W11, and see what we end up getting. So obviously the derivative will be with respect to the total error, and the total error in this case is this whole expression here. This whole expression here is the total error, and this is essentially just equal to MSE, right? That's what I'm going to call it. I'm going to call it MSE because it's the mean squared error for the whole output. So the derivative of the mean squared error, which is a total error, with respect to the derivative of weight 11. Okay, and at the end of the day, suppose we could calculate this little thing here. Suppose we could calculate this, which we can. What would we get at the end of the day? Well, at the end of the day, we would essentially just get an output called W11 prime. So this W11 prime is actually just a delta value that we can subtract from our actual W11 and see a rate of change which would make the output have an error of 0. Okay, because that's the change that we're looking at. But obviously we're not going to do that. We're going to be multiplying the W11 by a small learning rate, and actually then update our weight. So the actual weight updation will actually look like this. So W11 is so the new W11 is equal to W11 minus the learning rate, which is just going to be a small number, times W11 prime. So if we could somehow calculate this W11 prime, then all we have to do is just use this little formula over here to update our weight W11. So now let's break down this chain rule. As you will notice that the mean squared error for the derivative of W11, so the mean squared error actually has two parts. It has the initial O1 minus Y1 divided by 2 plus the O2 minus Y2 divided by 2. So the derivative of mean squared error of output 1, right, which is essentially the first part of the formula, this part, right, the first part of the formula, with respect to derivative of weight 11, plus the derivative of mean squared error of output 2 with respect to derivative of weight 11. Well, just by looking at the little diagram, I can tell you right away that this expression will immediately go to 0. It's not even worth our time computing this, because you can just see it visually. Just look at it. W11 is connected to output 1. It is not in any way affecting output 2 at all. So if we were to expand this using chain rule, what we would end up finding is that it just goes to 0. We'll just eventually find that, because output 2 is not in any way connected to W11, nor is it affected by it. So the change that the W11 affects on the mean squared error for output 2 is just 0. So now instead of writing MSE of output 1, let's write the actual little formula, which is O1 minus Y1 squared divided by 2. So the derivative of O1 minus Y1 squared divided by 2 with respect to the derivative of weight 11. If you think about it, we can just treat O1 minus Y1 as an x. So x squared divided by 2 just ends up being x, right? Because you bring the 2 out and subtract the power by 1. So essentially what we're going to be doing is this 2 over here is going to be subtracted by 1, and we're going to bring this 2 out and multiply this whole top part by 2, which just leaves us with the 2 cancels out, and which just leaves us with O1 minus Y1. So the derivative of O1 minus Y1 squared divided by 2 with respect to weight 11 is essentially just O1 minus Y1 multiplied by the derivative of the inside. So Y1 here is just a constant, so the derivative of the inside would obviously be the derivative of O1 minus the derivative of Y1 with respect to W11. But since Y1 is just a constant, the derivative of that immediately will go to 0. So essentially what we're just left with is the derivative of O1 with respect to W11. Now we have to kind of open up O1. It's not really O1, right? It's actually, O1 is technically right over here if you can see it. O1 is the tan H of the before activation of O1. O1 is the activated part of the neuron. So O1 is kind of just, I'm going to rewrite this formula as O1 minus Y1 times the derivative of the tan H of the before activation of O1 divided by d of W11. Well, what is the derivative of tan H of BO1? So just treat BO1 as like an X. So what is the derivative of tan H of X? I have the formula right over here, right? It's 1 minus tan H squared of X times the derivative of X. So essentially what this is going to end up being is O1 minus Y1 times 1 minus tan H squared of BO1 times the derivative of BO1 with respect to the derivative of weight 11. That's essentially what it ends up being. O1 minus Y1 times 1 minus tan H squared of BO1 times the derivative of BO1 with respect to the derivative of weight 11. So now what we need to do is expand this BO1 part. So BO1 is essentially just this H21 multiplied by weight 11 plus H22 multiplied by weight 12. And I'm just going to call it BO1 prime because I want to do BO1 prime down here. I don't want to do it on the same line just because I don't have enough space. So BO1 prime is equal to the derivative of, so BO1 prime is essentially the derivative of this guy, H21 times weight 11 plus H22 times weight 12. So H22 times weight 12 has absolutely no effect on weight 11. It has absolutely nothing to do with weight 11. This is kind of like saying 5 times x plus 7 times y, and you're taking the derivatives with respect to x, so that means the y part of the portion of the equation just immediately will go to 0, right? So the derivative of BO1 with respect to weight 11 is essentially just H21, right? Because this is kind of like saying 5x, and what is the derivative of 5x? It's just 5, right? So finally our equation just ends up looking like this: O1 minus Y1 times, by the way, this tan H squared of BO1 is essentially just O1 multiplied by O1. So O1 squared, 1 minus O1 squared times H21. That's pretty much our formula. This right here is equal to W11 prime, that prime value that we were looking for to update our weight 11. And guess what? Calculating the prime value for weight 12 is just as easy as this. So if we wanted to calculate the prime value for weight 12, essentially what we would be doing is everything would stay the same, but so this whole thing would stay the same, but instead of h multiplying by H21, right, because this part of the equation right here went to 0. So this part of the equation went to 0. If we were trying to calculate the derivative for weight 12, it would be this part of the equation that goes to 0. This part of the equation would not go to 0, and thus we would just be left with H22 is equal to W12 prime. Once we have this one little value over here calculated, we can calculate all the prime values for that neuron. So in this case, it was for the output 1 neuron that we're able to calculate all the prime values. So now we have the prime values for weight 11 and weight 12, which are connected to the output 1 neuron, right? So these are both connected to output 1, and you can see that here, right? See, weight 11 is connected to output 1 and weight 12 is connected to output 1. So what about weight 13 and weight 14, which are connected to output 2? What do you guys think if we were to do that whole chain rule thing again? What do you think this would end up being essentially this output 1 part would just be output 2. The delta for W13 would essentially just be output 2 minus y2, because now this will be the derivative for the mean squared error of 2, whereas the derivative for mean squared error of 1 would go to 0, because weight 13 is in no way affecting output 1, right? Because weight 13, as you can see here, is not even attached to output 1, so it wouldn't affect it. So the derivative for mean squared error of output 1 would go to 0, multiplied by 1 minus O2 squared multiplied by H21 is equal to the delta for weight 13. And just as easy as that, O of 2 minus y of 2 multiplied by 1 minus O2 squared times H22 is equal to delta for W14 prime. So let's take a look at this. I mean, can we generalize this formula just a little bit more? This part right here, by the way, this little thing over here, since we have to compute it over and over again, we obviously don't want to keep taking the derivative of these things, because for every single neuron, suppose there were 100 neurons, would we calculate this part over here over and over again, or would we just calculate it one time and then save it? So essentially what we could call this over here is, we could call it just an array of gamma of output 1 and the gamma of output 2. So this part up here is the gamma of output 1, and this part over here is the gamma of output 2. And once we have it calculated one time, we can just save it in an array. Calculating the derivative of the BO1 and BO2s is actually kind of easy too. So what I want to know is, what is the index of W11? Well, let's take a look at our diagram up here. So the index of W11 is actually 0, because the W11 is the first index that's connected to the output layer of output 1, and W12 is the first index at index 1. So W11 is the 0th index and W12 is the first index, right? And take a look at what H21 is. H21 in its hidden layer is actually the 0th index, whereas H22 is actually the first index. So we can see that there's a one-to-one corresponding with the index of the weight that we're trying to calculate the derivative for, and the index that the derivative of the before activation that it ends up computing. So H11 you can see is at index 0. So W11 you can see is at index 0, and H21 is also at index 0. Let's see, W14 is at index 1, right? W14 you can see that's at index 1, whereas W13 is at index 0. So W14 here is at index 0, and this H22 is also at index 0. So we don't even have to calculate the derivative for this. We can just directly find it right away. And that's going to save us a lot of computational time, because we're not going to be sitting there calculating derivatives. We've already found this really beautiful pattern matching that we can just do in code at constant time, basically. So now what we have actually learned is this really beautiful little formula. Okay, this formula right here will allow us to calculate the prime values for any weight in the output layer. So the I over here is the index of the weight in that neuron. So what is the index of the weight? So W11 you can see is at index 0 in the output 1 neuron, and W12 is at index 1 at the output 1 neuron. And the X is and the X over here is what is the neuron that this weight is connected to. What is the index of the neuron that this weight is connected to? So W14 is connected to the 1 index neuron, which is output 2, right? Output 2 is at index 1 in the output layer. So just as an example, let's pick W12 and see how we can calculate this. So W12, what is the I value for W12? So let's see. W12 is connected at the first index. So the I value for W12 is going to be 1. And what is the X value? What is the index of the neuron that it's connected to? In this case, X is going to be 0, because it's connected to output 1, right? Is equal to, we have the X now, so that's gamma of 0, which makes sense. It's gamma of 0 is basically the gamma of output 1, right? Well, where do we calculate? Right here, right? So yeah, that makes sense. It's the gamma of output 1. multiplied by h of I. So we said I is equal to 1. So what is the first index neuron in the previous layer? It's h22 right here, right? Times h22. With this formula right here, we can calculate delta values for any weight that we want in the output layer. One thing that you guys also start to notice is that we can start using these gamma values in the hidden layer, and I'm going to show you guys that right now, and it's actually going to make our calculations infinitely easier. But now can we come up with a formula for the hidden layers where we can use some elegant formula like that to find the delta for any weight in the hidden layer. So when I'm doing these derivation processes, you should be looking for basically patterns. The whole point here is to make our computation when we actually write the code as easy as possible, because we don't want to be taking derivatives of this layer with respect to the layer in the forward layer, and then that respect to the forward layer. You know, that's too much work. That would, you know, the complexity there would be extremely high. So when we take the derivative of weight 1, we want it to be the same complexity for weight 1 in terms of computation time as if we had taken for weight 7, right? Or if we had taken for weight 11. So I think we should just start by trying to find the derivative of weight 7 and see what happens. So now when I do the derivation process, I'm actually not gonna expand each individual components. I'm actually just gonna unroll with a chain rule. Like, I'm just gonna call it mean squared error, you know, maybe of output 1, but I'm not gonna replace it with output 1 minus y1 squared over 2, okay? Because then that'll just fill up the whole page, and we want to keep things as simple as possible. Also notice this is actually a pretty cool example of the chain rule and what it means to be backpropagating. So check this out. Weight 7 actually affects, let me use the yellow color. Weight 7 actually affects this hidden neuron here, H21, right? H21 in turn actually affects the output 1, and it affects output 2. Thus, weight 7 actually indirectly affects both output 1 and output 2. So, you know, previously when we took the derivative for weight 11, right, weight 11 only affects output 1, but not output 2. So when we took the mean squared error with respect to the derivative of mean squared error with respect to weight 11, we only took this component because weight 11 never affected output 2, so thus this part of the component ended up going to 0. But in this case, now, weight 7 actually does affect both output 1 and output 2. So we need to take the derivative of mean squared error of output 1 with respect to weight 7, so which would be this part. And we need to take the derivative of mean squared error of output 2 with respect to weight 7. And basically we're going to add the two derivatives up. So in this case, since weight 7 actually indirectly affects both output 1 and output 2, we have to take both components is actually equal to, right? See, we have to take both these components, output 1, mean squared error of output 1, and mean squared error of output 2. So the derivative of mean squared error of output 1 with respect to weight 7 plus the derivative of mean squared error of output 2 with respect to weight 7. Okay, so now let's just tackle this one at a time. So I'm just going to expand this guy, okay? So let's see, the derivative of mean squared error of output 1 with respect to weight 7 equals, so what the chain rule will tell us is the derivative of mean squared error of output 1 with respect to derivative of weight 7 is actually the derivative of mean squared error of output 1 with respect to the derivative of output 1. Once again, because the output 1 is the only component within the derivative of mean squared error of output 1 that we're able to take the derivative of, because the derivative of y1 is just 0, times the derivative of output 1 with respect to the derivative of the before activation of output 1, right? Once again, that's because output 1 is actually the tan h of before activation of output 1. So once we're done taking the derivative of tan h of before activation of output 1, we then have to take the derivative of the inside, which is before activation of output 1. So the derivative of the before activation of output 1 with respect to, so now we have to take the derivative before activation of output 1 with respect to h21, because h21 is the neuron which connects to before activation of output 1. Okay, now and then we have to take the derivative of h21, and we have to take it with respect to the before activation h21. Just similarly like this guy over here, we have to do the same thing over there. So the derivative of the before activation of h21. And now finally we have to take the derivative of the before activation of h21 with the final component, the derivative of weight 7. Okay, that's the chain rule. We just expanded this guy with the chain rule. And let's just look at it from the graphical point of view. We're taking the derivative of mean squared error of output 1 with respect to output 1. And then we're taking the derivative of output 1 with respect to before activation of output 1. And then before activation output 1 with respect to h21, h21 before activation of h21, and finally weight 7. That's the chain rule, right? We're kind of like just chaining them together. We're just slowly expanding and unrolling this chain rule out because each of these components in turn are the parameters, I guess you could kind of look at it. So now what we need to do is unroll mean squared error of output 2. And when I unroll mean squared error of output 2, you'll actually start to notice similarities between the unrolled chain rule for this one and this chain rule over here. And we'll actually start to see how we can simplify these two additions down even further. Well, first of all, you should almost immediately notice how this part of the formula right over here is pretty much exactly the same, is it not? This part of the formula is pretty much exactly the same. Well, another thing you should almost immediately realize is this part over here, this part right over here, is actually just gamma of output 1 of the previous neuron, right? And this part over here is kind of just gamma of output 2. We're finding these gamma values that we've already calculated in the forward layer, this layer, right? The output layer, we're finding the gamma value G01, and we found the gamma value of G02 and this expanded derivative. What is the derivative of B01 with respect to H21? Well, that right there is actually just weight 11, right? What is the derivative of before activation of O2 with respect to H21? Well, this is just weight 13. We took the derivative of before activation of output 1 with respect to H21. The derivative would just be weight 11. And we're taking the derivative of before activation of output 2 with respect to H21, and the derivative there would just be weight 13. Gamma of output 1 and gamma of output 2 we've already calculated before. Weight 11, weight, and 13, I'll actually show you guys how we can find that super easily using that index idea. What we should first do is actually try to take the derivative of this little box over here. So now what we want to take is the derivative of H21 with respect to before activation H21 multiplied by the derivative of before activation H2 with respect to weight 7. The derivative of H21 with respect to before activation H21 is like saying the derivative of output 1 with respect to the before activation of output 1. Well, that in that case, which wasn't it just 1 minus or output 1 squared? So in this case, it would just be 1 minus H21 squared. Multiplied by the derivative of H21 with respect to weight 7. That's almost just like saying the derivative of before activation of output 1 with respect to weight 11, which was just H21. In this case, it would just be the derivative of before activation of H21 with respect to weight 7 would just be H11. So I have just rewritten the derivative of mean squared error with respect to weight 7, what we just calculated back here. So all you need to really know is that gamma of output 1 is in the forward layer, and gamma of output 2 is also in the forward layer. So weight 11 and weight 13 are actually the connections of output 1 and output 2 that connect to H21. We have to take the derivative of the actual neuron itself times the derivative finally of the before activation of that neuron with respect to weight 7. So let's pick another weight in hidden layer 2 to take the derivative of, and we'll see how we can use this little trick that we've just learned to find the derivative of it, mean squared error. So let's take the derivative of weight 9. Alright, let's take derivative of weight 9. Of derivative of weight 9. So we know that we're going to end up getting gamma of output 1 and gamma of output 2 because that's just what the chain rule will end up giving us. So we can almost already put that in here. Gamma of output 1 plus the gamma of output 2. Let's take a look at weight 9. Weight 9 actually connects to this neuron over here, H22. So we know that we're going to have to end up taking the derivative of that neuron. So, which is going to just be 1 minus H22 squared. What is the neuron weight 9 is connected to in the previous layer, which is H11. So once again, we bring H11 down here. So what is the connection, just like up here with weight 11, which was connecting to H21? What is the connection here in gamma of output 1? Well, that connection is simply weight 12. So output 1 is connected to H22 through weight 12. So how is output 2 connected to H22? It's weight 14. There you go. We just found the delta value for weight 9. Find the delta value for any weight that we want in any of the hidden layers, not just hidden layer 2. So now what we're going to do is call this value here gamma of H21, and we're going to call this value here gamma of H22. And the reason for that is because if we wanted to compute the derivative for any of the weights that is connected to H21, we're going to have to use this gamma value again, similarly to the output layer, because H21 has other weights that are connected to it. So if we wanted to find the delta value for weight 8, this value would need to be computed again. And this gamma H21 value and this gamma H22 value are now the gamma values for H21 and H22, and that would help us a lot when we try to find the derivative of mean squared error with respect to weight 5. The derivative of mean squared error with respect to weight 5 would actually end up being the gamma of H21, right, times some value, we'll worry about that later, plus the gamma of H22 times 1 minus H12 squared multiplied by I2, because I2 is the connection in the previous layer. So what is the connection to H12 from H21? So that is weight 8. So what is the connection to H22 from H12? That's weight 10. There you go. So with this, so if we had the gamma of H21 and the gamma of H22 calculated, we could easily calculate the delta for weight 5. And we will have the gamma of H21 and H22 calculated, because we would obviously compute the delta values for the hidden layer 2 before we calculate the delta values for hidden layer 1, because we're trying to streamline the process. We're not trying to do this giant chain rule calculation. We've already calculated the gamma values in the forward layer, because in the forward layer we had to calculate the delta values there. So now we're just using the gamma values that were previously calculated to update the weights in this hidden layer. And once again, you should immediately be able to know that this part over here is actually now the gamma of H12, right? The gamma of H12 will have to be used again for all the connections that are connected to H12, such as weight 6 and weight 4. So now I've just written down a formula that will allow us to update any weight that we want in any of the hidden layers. But first, let me just go through some of these terms. The I is the index of the neuron that it's connected to. So next, Z is the index of the weight within that neuron. So that's I and Z. F is the number of neurons in the forward layer, -1, because we want to deal with indices and we start from the 0th index, okay? G of X is the gamma value in the forward layer. Now we know what the X is. X is just iterating through all the neurons in the forward layer. This over here will actually allow us to find that connection that connects to this neuron. So H of I is the neuron that this weight is connected to, times HZ, which is the neuron in the previous layer. Derivative of mean squared error with respect to weight 6. So we have to convert weight 6 into its IZ component. so that we know where it is in terms of positional space in the neural network. So the I value for weight 6 would be 1 because it's connected to the first index neuron, which is H12. So I would be a 1 and the Z would be a 2. Remember, because it is the second index in H21. You can also look at it as it's connected to the second index in the previous hidden layer. We know that F is 2 because there are 2 neurons in the forward layer, right? There's 2, H21 and H22. Once again, H of I is the connection that weight 6 is connected to, which is H12. So it would be H12 squared. And Hz is the connection in the previous layer, which is I3. So now we need to unroll this guy over here. So the gamma value for H21 times some weight plus the gamma value for H22 times some value. We know that I is 1, so we know that first X is going to be 0. Because this gamma could also be just looked at as gamma 0. This gamma could also be looked at as gamma 1. So when X is 0, we're targeting this neuron, the 0th index neuron in the forward layer, and when I is 1, it's weight 8. So weight 8. When X is 1 and I is 1, that's weight 10. Weight 10. Now let's get into what our data structures are going to look like. So in my previous video, I had everything in just one neural network file, but this time we're going to have 2 neural network files. One is going to be like the main neural network file, but then we're also going to have another file called neural network layer. So we're going to need a float matrix, just a simple one-dimensional matrix, which will be the output values of any given layer. So, H11, H12, right, is equal to new float. New float. That's going to be the size of the float matrix, or the number of neurons in that layer. We're also going to need a weight matrix. It's going to be the weights is equal to new float. The first parameter will be the number of neurons in the layer, comma, number of neurons in previous layer. We're actually going to need 2 of these, so one for the weight and one for the delta values for the weight. Next thing that we're going to need is the gamma matrix. So float gamma is equal to new float, and this is just going to be the number of neurons in the layer. This is just a special little thing that we're going to need for the output layer, because we're going to be calculating our the derivative of our mean squared error for the output layers. Each layer will have this data structure to keep track of. With these simple 5 data structures, we can do back propagation and in forward propagation. So I'm going to be programming this in C# in Unity, but you can do it in C# in any other development environment you want. But if you're using Unity, just click New. I'm just going to call this, hopefully that's how you spell tutorial, and then just click Create Project. Once it's open, just create a new folder called Neural Network. Just create a file called Neural Network and open it. Once the file is open, you can just remove these not needed imports. We're going to need another class within this neural network called Layer. You can have a completely separate class if you want, but I'm not going to do that. I'm just going to have everything in here. So let's create a constructor for neural network. So this neural network is going to be taking in a layer information. So because we want to be able to create neural networks of any layer size, once we're done deep copying this layer, we're probably going to need to create a bunch of these layer classes. So now let's also create this layer object up here. So layers. The layers is equal to new layer. And the size of these layers is going to be, because once again we're going to be ignoring the input layer, so it's going to be the layer.length -1. Now let's work on our layer class a little bit before we initialize the objects in this layer array. We're going to have to write some data structures that I talked about before. So this is going to be the number of neurons that are in the previous layer because they are the incoming connection. So this is the number of neurons in the current layers. We're also going to need the data structure for number of outputs. We're also going to need inputs. We're going to also need the weights, need the delta values for the weights, so that we can update our weight matrix. Weights delta. Let's see, we're also going to need the gamma. So this is going to be for the output layer only. We're going to need the error. So with these 6 data structures, we should be able to do feed forward and back propagation. Now let's initialize outputs. So the size of the output is obviously just going to be the number of outputs, and similarly the size of the inputs is just going to be the number of inputs. The weight matrix is going to be the number of output, all the possible connections that it can make in the previous layer. Delta weight is the exact same. Our gamma is the exact same as the output. Oh, my bad, I accidentally added this comma. Just remove the comma from the gamma and the error. And the error is the exact same as gamma, the number of errors in the current layer for the output layer only. So we can now actually create the object of layer in our neural network class. So now we have to pass in the number of inputs and the number of outputs. We can get that information from this layer, the layer at I, right? That's the number of inputs that we're passing in. And the number of outputs, it's going to be layer at I plus 1. Now that we're done initializing our layers, we're going to have to now work on feed forward. So let's do feed forward first. So we're going to have to first write our feed forward in the layer class because we need to feed forward this specific layer. So this feed forward is going to have to return something, and it's going to be returning the output. So each layer has to return the output once it's done feed forwarding of some input layer. So it's receiving an input, and it's gonna feed forward that input. So we're gonna have to first initialize this input as our current input. First thing that we're gonna be doing is iterating over all the neurons in this current layer. It's equal to 0 because we're gonna be computing it from scratch again for each feed forward. So now we're iterating over all the neurons in the previous layer. So we're getting that weight value for each neuron, which is connected to some neuron in the previous layer. We're going to be using math.tanH, and we're going to be passing output at I through it. We are done our feed forward. For the layer, our neural network class, we're going to have to write a feed forward method. What we're going to be returning as the array is going to be the last layer's output values. We need to pass this input into the first layer of the layer. And now what we need to do is iterate over layers. Starting from index 1, we need to feed forward these layers. And the feed forward obviously needs to get outputs of the previous layer and pass them as the input. The layers at I minus 1 dot output. So this right here will now feed forward our entire neural network. So the one thing that I actually forgot to do was initialize weights values. Initialize these weights to some random number between negative 0.5 and 0.5. Iterate over all the weights. We need a random class to be able to do this. So it's just going to be initialized, since it's a class property, it's just going to be initialized once. Now initializes our weights between negative 0.5 and 0.5. Let's just call this initialize weights. In our layers constructor. So before we do the back propagation, let's just write a simple function that updates our weights for us. We want to be able to subtract those delta values from our weights. We're obviously not going to be subtracting the entire delta. We're going to be subtracting some multiplied by some learning rate. I'm just going to hard code learning rate, definitely make this into a variable later. We're going to need 2 different methods. So if this layer is an output layer, we call this, and if this layer is a hidden layer, we're going to be calling this. So now let's get into the back propagation for the output layer. First thing we should be doing is actually calculating this error value. We don't even actually need this array, but I only made it just because it'll make things a little bit easier to understand. We need to calculate the derivative of the error, which is actually just literally going to be output minus the actual value. Derivative error at I is equal to the output at I minus the expected I. Error at I now contains the total mean squared error with respect to the output. So now let's calculate our gamma values. So before we actually calculate the gamma values, let's create a function which will calculate the derivative of the tanH. And essentially what it's going to do is return 1 minus the value squared, so value times value. Gamma at I is equal to error at I multiplied by derivative of output. And this is quite literally that gamma formula that I was showing you guys. Now what we need to do is actually calculate the derivative for every single weight in the output layer. Delta weight at I comma j is equal to gamma at I multiplied by inputs at j. If you didn't care about any layers and you only wanted to train the output layer, you could just run this with an expected value and train the neural network. Will take two parameters, gamma of forward layer and the weights of the forward layer. So that's basically what our backpropagation for the hidden layers needs. First thing that we need to do is iterate over all the gamma values in this current hidden layer, and we probably should just zero out the gamma value. And now we need to iterate over every single gamma value in this forward layer, and now we're iterating over every single gamma value in the forward layer. So the gamma value in the forward layer, j, multiplied by the weights in the forward layer, j, I. We need to also take the derivative of the output of this current layer, so that would be gamma at I times equal tan derivative output. Now we've basically just calculated our gamma value for this hidden layer, and we can literally just copy paste this little bit of code to get our new delta weight values for this hidden layer. Just paste them here, and we're pretty much done. Just these two methods now takes care of our whole backpropagation algorithm. Just like this feed forward, we need to write a backpropagation method, and it takes an expected value. So now we just want to iterate over every single layer, but we actually want to iterate backwards. We want to check if the current layer is an output layer. Layers at I.backprop output, pass in expected, otherwise backprop hidden. In this, we're gonna have to pass in the gamma values, the layers at I plus 1, right, the forward layers, and we're gonna have to pass in forward layers weights. And one final thing that we have to add now is we have to iterate over all the layers and actually update the weights. Update weights, this is supposed to be a 0, starting from the first index. That's it. Our backpropagation is now complete. We can go ahead and actually test this out now, see if it actually works properly or not. So I'm going to now create a new class, and I'm going to call it tester. I'm just going to test a XOR with 3 values. So if you've never done XOR before, this is basically the XOR table. To be able to learn this XOR, the network really doesn't have to be that big. 3, so this is our number of inputs, which is 3, and I'm going to give it 225 neuron hidden layers, and then finally the output is 1. Oh, my bad, I'm actually putting this inside square braces. So now I've just written this little for loop that iterates over 5,000 times. It's basically going to be training the network 5,000 times 8 times. So first we're feed forwarding the network with some inputs. Feed forward is basically generating an expected output, right? And then we're basically backpropagating the correct output. So in this case 0, 0, 0. The correct output is 0, so we're backpropagating that, and the network is basically just going to take what it already expected the output to be versus this correct output and backpropagate the error, and hopefully our network will learn to be able to basically predict this table. So now after we're done training our network, I'm just doing the same feed forward again, and since we only have one output, I'm just going to print out the output at the index 0. Let's see how this thing is able to predict the output. Take this tester class and actually, well, why do I have missing scripts? Remove. Okay, just take this tester and just put it in the camera. Click the run button, and it's print the output 0. That's pretty good. 0, 1, 1. Well, it's not really 1. It's 0.94, right? But we can actually fix that by increasing our learning rate and seeing what happens. So 0, 1, 1, 0. And then 0.9, and then 1, 0, 0, 1. So it's doing pretty good. So let's increase our learning rate and see if we can actually lower the error even further. And I'm just going to multiply this learning rate by 10. So instead of 0.003, it's going to be 0.03. Run this again. Wow, this time we can see that it's learned it even more. -4 to the power of -5, that's a pretty small number, I would say. Pretty much our network has learned this XOR table, and that means that our neural network is actually working properly. So I hope that this tutorial was useful in trying to learn backpropagation for neural network. If you have any questions, just leave it in the comments, and I will be answering them. Anyways, thanks for watching. Bye.